Koshi Condensation. Let's think back to the Harmonic Series. Well, here's the Harmonic Series, and we proved that it diverges. And how do we do that? Well, we did this grouping trick. Here's the beginning of the Harmonic Series, and it keeps on going. And what we saw was that we've got a 1 here and a half here. This third and this fourth can be grouped together, and the next 4 terms can be grouped together, and then the next 8 terms will be grouped together, and so on. But this group here is at least a half, because it's 2 terms that are each at least as big as a fourth. This next group here is also at least a half, because it's 4 terms that are each at least an eighth. And then the next group of 8 terms is at least a half, and the next group of 16 terms is at least a half. So this is even worse than adding up 1 plus a half plus a half plus a half plus a half plus a half, and that series diverges. So we're able to show that the Harmonic Series diverges by doing this grouping into piles with sizes the powers of 2. This isn't just some one-off trick. This is a technique that we can generalize and then apply broadly. Now, we used it for the Harmonic Series to show that the series diverged, but we can also use the same kind of thinking to show that a series converges. Well, the name for this trick is Koshi Condensation. Here's how it goes, at least when using it to prove convergence. So let's suppose that I've got a decreasing sequence and that all of the terms are positive. I want to know, does this series, the sum k goes from 1 to infinity of a sub k, converge or diverge? I can group them by powers of 2. So what I mean is I'll put a sub 1 by itself. I'll group together a sub 2 and a sub 3. I'll group together a sub 4, a sub 5, a sub 6, and a sub 7. I'll group a sub 8 alongside a sub 9, a sub 10, a sub 11, a sub 12, a sub 13, a sub 14, a sub 15. And then I'll group a sub 16, a sub 17. I'm going to keep on going until I get to a sub 31. And then I start a new group at a sub 32. Now I'll overestimate the groups. Well, how big is a sub 2 plus a sub 3? The key fact here is that the sequence of the a sub k's is decreasing. That means that a sub 3 is smaller than a sub 2. So if I add a sub 2 and a sub 3, the result is less than twice a sub 2. What about this next group? What's a sub 4 plus a sub 5 plus a sub 6 plus a sub 7? Well, a sub 5, a sub 6, and a sub 7 are all less than a sub 4, again, because the sequence is decreasing. So if I add these 4 numbers up, the result is less than if I just multiplied the 4th term by 4. What about the next 8 terms? Well, these terms from a sub 9 through a sub 15 are all smaller than a sub 8. So these 8 terms altogether are less than just 8 copies of a sub 8. And it keeps on going, right? The next 16 terms, if I were to group them all together, would be less than 16 copies of a sub 16, and so on. Let me write down a precise statement of what we're doing. So here's how I can write down the grouping in symbols. Let's look at the sum of the a sub k's. K goes from 1 all the way up to 1 less than a power of 2. So 2 to the n minus 1, say. So this would be like adding up the first 7 terms, or the first 15 terms, or the first 31 terms. It's a collection of terms where I can actually do the grouping. Well, this is less than or equal to then the sum of what happens after I do the grouping, right? Which is 2 to the k times a sub 2 to the k. This is what I get when I do this grouping. K goes from 0 all the way up to n minus 1. Why is this significant? So we were originally interested in studying this series and determining whether this series converged or diverged. And now we're led to studying this series, the sum k goes from 0 to infinity of 2 to the k times the 2 to the kth term in the sequence. I'm going to call this series the condensed series associated to this series. Now, what if the condensed series converges? So if this condensed series converges, right, then what happens? Well, recall what I know, right? This condensed series is overestimating the original series. So if I'm trying to study something about the partial sums of the original series, what I know now is that those partial sums for the original series are bounded above by the value of the convergent condensed series. I also know that the partial sums for the original series are increasing. And that's just because all of the a sub k's are positive. So as I add up more and more of the a sub k's, I'm getting a bigger and bigger number. So the sequence of partial sums is increasing. That means the sequence of partial sums is bounded above and increasing and therefore convergent. And what that means then is that the original series that I'm interested in converges. Let's summarize the theorem. So here's a statement of the Koshi condensation test. If you've got a sequence which is decreasing and all of the terms are positive, then the series, sum k goes from 1 to infinity a sub k, converges if the condensed series converges. That's what we've just proved. And in fact, it's an if and only if. So the fate of the condensed series is exactly the same as the fate of the original series.